Welcome back to Next Gen Manufacturing. Now, I want you to think about the metal things all around you. Your car door, a file cabinet, even a simple soda can. You'd probably guess they were cast from molten metal or maybe carved out of a big solid block. But you'd most likely be wrong. See, almost all of them started out as something much simpler, a totally flat sheet. No, really, just for a second, look around you. The case on your computer, the shell of your microwave, that license plate on your car. Sheet metal is, without a doubt, one of the most essential but overlooked materials that literally shapes our world. So the big question is, how does a flat sheet get its shape?
And we're talking about pretty much everything. I mean, from the massive body panels on airplanes and trucks, all the way down to the appliances in your kitchen and even a basic cooking pot. All these things are so common because they're incredibly strong, they're precise, and they're relatively cheap to make. And that's all thanks to the magic of sheet metalworking.
So what exactly are we talking about here? Well, at its core, sheet metalworking is all about cutting and forming metal that's pretty thin, usually less than 1/4 of an inch thick. You know, if it gets any thicker than that, we stop calling it a sheet and start calling it plate. And most of these processes happen at room temperature, which is why you'll often hear them called cold working. So to really get a handle on this huge and super diverse field, we can actually break down almost every single operation into just 3 basic fundamental transformations. This is the secret sauce. It's how we go from a boring flat sheet to a complex, useful part.
It's a simple recipe, really. First, you've got to cut the metal into the basic shape you need. Then, you bend it to create angles and give it some real structure. And finally, for those more complex shapes like a sink or a can, you draw it to create depth. Cutting, bending, and drawing. So, let's break them down one by one.
Okay, first things first, cutting. Before you can bend or form anything, you have to separate your piece from a bigger sheet or a giant coil of metal, and that process is called shearing.
Now, what's really wild is that this whole shearing thing happens in the blink of an eye. But if we could slow it way down, this is what you'd see. First, the punch presses down and just deforms the metal a bit. Then it penetrates, cutting maybe about 1/3 of the way through. That pressure starts a crack from the top edge and the bottom edge. And if everything is set up just right, those 2 cracks race toward each other and meet perfectly in the middle for a clean break.
Now, inside the world of cutting, there are 2 key operations that sound alike, but they're actually total opposites: punching and blanking. Think of it this way. With punching, you're making a hole. The sheet is your part, and the little piece you cut out, the slug, that's the scrap. With blanking, it's the reverse. The piece you cut out, the blank, that's your part, and the sheet around it is the scrap. It all just comes down to which piece you're planning to keep.
So the real secret to a perfect clean cut is this one little thing called clearance. It's the tiny gap between the punch and the die. And no, it's not like a pair of scissors where the blades touch. This space is put there on purpose, and getting it right is absolutely critical. Because getting this clearance right is everything. If the gap is too small, those fracture lines we talked about won't meet up cleanly, and you have to use a ton of extra force. But if the gap is too large, the metal kind of gets pinched and torn instead of sheared, leaving this nasty, sharp edge called a burr. That perfect clearance, we're talking just 4 to 8% of the metal's thickness, is the key to a beautiful cut.
All right, let's move on to our second transformation. Once we have our flat blank all cut out, we need to give it some strength and structure, and we do that through bending.
Okay, so when you bend a piece of sheet metal, something really cool happens inside the material. The metal on the inside of the corner gets squeezed together. It's compressed. At the same time, the metal on the outside of the corner gets pulled apart. It's stretched. And right in the middle, there's a line called the neutral axis that isn't doing either. This internal stress is what locks in that permanent shape.
But here's the catch. Metal has a memory. After you bend it and let go, it wants to return to its old flat shape just a tiny little bit. This elastic recovery is called springback. So you might bend a part with a perfect 90-degree tool, but when you pull it out, it relaxes to, say, 92 degrees. And in next-gen manufacturing, 2 degrees isn't a small error. It's a disaster. That's the difference between a car door that seals perfectly and one that whistles like crazy on the highway.
So how do you fight springback? Well, you outsmart it. Engineers use these really clever techniques like overbending, where they'll actually bend the part to 88 degrees, knowing it'll spring back to a perfect 90. Or they'll use a method called bottoming, where they give the metal an extra hard squeeze at the end of the press stroke to kind of shock the memory out of it and set the bend for good.
All right, on to our final transformation, and this is where we go from 2D to full-on 3D.
How in the world do you take a flat, circular piece of metal and turn it into something deep and seamless, like a cooking pot or a soda can? The answer is a process called drawing.
Drawing is where a punch literally forces a flat sheet metal blank down into a die cavity. The metal isn't just being bent here, it's being forced to flow and stretch and compress all at once as it gets pulled into this new 3D shape. It is, without a doubt, the most complex of the three core processes.
So, to figure out if you can even make a deep part without it ripping apart, engineers use a critical measurement called the drawing ratio. And the magic number is right here, 2.0. This ratio compares the size of the flat disc you start with to the size of the punch that forms it. If that ratio gets much bigger than 2, you're asking the metal to stretch too far, too fast, and it's pretty much guaranteed to fail by tearing.
And trust me, a lot can go wrong. If the forces aren't balanced perfectly, you can get wrinkling in the walls, you could get tearing near the bottom where the tension is highest, or you could get something called earring, where the top edge becomes all wavy and uneven. It just goes to show you how much science is packed into making even the simplest looking can on the shelf. Okay, now that we've nailed down the big three, cutting, bending, and drawing, let's check out a quick bonus round of a few next-level forming processes that show just how incredibly versatile sheet metal can be.
First up, roll forming. Imagine a giant ribbon of steel, miles long, flowing through a factory. Instead of one big bend, this process uses a whole series of rollers that progressively and gently shape that continuous coil into a complex shape. If you've ever seen long pieces of metal siding or rain gutters, that's roll forming in action.
Next up is spinning, which is basically like a potter's wheel, but for metal. You take a flat metal disc, spin it at super high speed, and then a tool presses against it, flowing the metal over a mold, which is called a mandrel. It's the perfect way to make symmetrical, curvy parts, like the nose cone on a rocket or the bell of a trumpet.
And finally, we've got to talk about one of the most powerful and frankly, coolest methods out there, explosive forming. Yes, you heard me right. Explosives. You literally detonate a charge underwater, and the shockwave from the blast slams a huge sheet of metal into a die with unbelievable force and accuracy. It's the go-to method for making massive, complicated parts, especially for the aerospace industry.
So there you have it, from a simple shearing cut to a precise 90-degree bend to a deep, complex draw and even using an explosive blast. These are the invisible processes working behind the scenes. They are what transform simple flat sheets into the strong, lightweight, and affordable metal parts that build our modern world. So the next time you pop open a can, get in your car, or grab a pot from the kitchen cabinet, I want you to take a closer look. Will you just see a simple object, or will you see the incredible journey it took of cutting, bending, and drawing, the hidden engineering that gave that object its shape and its purpose?